So dear students, welcome to another lecture of Basic Electrical Engineering. In this particular lecture, we will discuss about the power factor improvement. So this lecture is on the introduction to the power factor, causes of low power factor, limitations of low power factor, and then we will see how we can improve the power factor and what are the benefits of improving the power factor, right? So what is power factor? Now, before we understand the power factor, what is power factor, we need to understand some basic terms which are associated to the power factor. The first is kilowatt. The first term which you see here is kilowatt. So kilowatt is basically the unit of actual power, or you can say reactive power or real power, or we can say working power, right? So when we talk about the power triangle, or when we talk about the power, so power is apparent power, right? So we have apparent power. Apparent power is the power of the source. Then this apparent power has two components. One is the active power and second one is the reactive power. So this active power is the power which is actually utilized or used by the load connected to the electrical system. And the power which is not utilized or used by the load remains stored in the reactive components which are connected into the electrical systems, and such reactive components are like the inductive components, right, like transformer, motor, or any other inductive component, or let us say inductor itself, right? So this power we call as the reactive power, and this power is measured in kilovolt ampere reactive. So it is kilovolt ampere reactive. Actually the unit is volt ampere reactive, but since the magnitude of the power for the power systems or electrical systems is quite high, so we generally measure this in kilovolt ampere reactive, right? So we have the working power, we have the volt ampere reactive, which is nothing but the reactive power, right? And this power, as I said, is because of the reactive components which are connected into the system, specifically the inductors or inductive components, right? And then we have the volt amperes, or you can say kilovolt ampere. So this is nothing but the apparent power. So this is the power of the source. That means the power which is generated, which is produced by the source, and this power is delivered to the load. But from this power, one component is utilized or used, or you can say dissipated, or utilized for some purposeful work, and the another component is not used, not utilized, not dissipated, rather it is stored due to the reactiveness of the electrical systems. So this is we are discussing because we know that the power factor is nothing, it is something which is associated with the uh, these three types of powers. Now we can better understand this concept through this power triangle which is shown here. Now this power triangle can be obtained from the phasor diagram of an inductive circuit. Let us consider our general AC circuit. So for any general AC circuit, let us consider that it is having a resistance, it is having some inductance in it, right? So this is a series RL circuit, right? This is a series RL circuit. Now, if capital V is the RMS value of the input voltage, V is equal to Vm sine theta, then if I is the RMS value of the current flowing through this particular circuit, then this resistance will have a voltage drop which is given by VR, where VR is the RMS value of the voltage drop across the resistance, and similarly VL is the voltage drop across the inductance, right? So when we draw the phasor diagram of the resistance between this VR and I will be same. So we have VR and we have I. So both are in same phase. However, in case of inductor, we know that the voltage across inductor will lead the current by 90 degrees. So in general, we can draw this like, so we have the voltage across resistance, we have the current, and then we have the voltage across the inductance which is leading this current by 90-degree, and then we have the resultant voltage V. So this is the angle phi, right? Now we can see that there are two major components. One is this voltage V, which is the RMS value of the input voltage, and another is this current I, which is the RMS value of the supply current or input current. So this phi is the phase difference between V and I, right? So here we can see that current is lagging V by phi, right? So this is the conclusion of this. Now, if we multiply this V by I, if we multiply this VL by I, if we multiply this VR by I, so this would be the power, but this is the volt ampere reactive power. This is the power, but this is the watt, the real power, and this is also the power which is nothing but the source power, right? Which we generally call as the apparent power, right? So this power triangle can be obtained from the voltage triangle of a general AC circuit, whether it is a series AC circuit or parallel AC circuit, doesn't matter, but we can get the power triangle from these AC circuits, right? So as you can see here, we have apparent power, which is measured in volt amperes. We have reactive power, which is measured in volt ampere reactive. Then we have the real power, which is measured in watts, right? So this is the power triangle. Now, what is power factor? So power factor, now from this we can get the power factor, because this apparent power is actually the resultant of two powers, the real power and the reactive power, right? So power factor is nothing but it is the cosine of, now if we talk about the same phasor diagram, V and I, the two components of series RL circuit, and the angle, the phase angle between them is phi. So cosine of this particular angle between the voltage and I, cosine of this angle is generally the mathematical expression of the power factor, but the power factor is nothing but it is the ratio of the real power or the working power to the apparent power, that is the total power. So we can say that the amount of power which is used for some work divided by the total power supplied by the source to the load is the power factor, right? And mathematically it is expressed as the cosine of angle between the voltage and the current in case of a general AC circuit, right? So this is the mathematical expression. So we can write that cos phi, which is nothing but the power factor. So power factor, which is nothing but cosine of the angle between V and I, is the ratio of active power or real power or working power or actual power to the apparent power, right? So this is what power factor is. Now this power factor plays a very important role in AC circuits, right? So as you can see here, um, if you have understood it clearly, right, or in a right way, so you will get that this is something which is the output, right? This is the output. That means the power which is actually dissipated, which is actually utilized, which is actually used by the load, right? And this apparent power is nothing but the input power, right? It is given to the system, it is delivered by the source to the system. So this is something we call as, we can relate this with the input, right? So we have output upon input. So this is something which also tells us about the efficiency of a system, right? Efficiency of the system. Ideally, ideally, active power should be equal to the apparent power, right? That means whatever power delivered by the source to the load, that power as it is must be utilized by the load, right? So indirectly what we are saying that no power, no part of power, or no percentage of this apparent power shall be stored due to any reactiveness of the system, right? So in this case, if this is the case, then we have cos phi is equal to 1 or phi is equal to 0, right? So this is only possible when uh, the load is pure resistive, right? So in case of pure resistive load, we can get this uh, response, this output. But even then also, it is very difficult, almost impossible to get the unity power factor. Okay, this is what we call as the unity power factor. So this is the ideal scenario. Okay, this is the ideal case, right? So this is itself is very difficult. So the reason is that we actually do not have the pure resistive electric circuits, right? Even if the load is pure resistance, then the source will have inductance. Definitely the source has inductance. So that inductive effect will create the lag in the current from the voltage, and this lag will lead to the increase in value of phi. So when phi will increase, obviously cosine phi will decrease, right? So we can say that if phi increases, cos phi decreases, right? So now let us come to the limitations of low power factor. Now, this is but obvious that the why the power factor is low. So the first question is why the power factor is low, right? So this is the question, right? So in case of inductive circuit, current lags the voltage by angle phi. So that means the phase difference between the voltage and current, right? So is phi, or we can draw it like this: I, V, and phi. So you can see the current is lagging the voltage by some angle phi, right? Now we are saying that cos phi is the power factor, right? So if the inductiveness increases, the current will lag the voltage, right, with more value of phi. So that means that is phi increases, right? Hence cos phi reduces. So it will reduce, right? So that means one thing is clear, that the primary reason, the major reason, the primary reason of the low power factor is the inductiveness in the circuit. It is the inductor, because it is because of the inductor or inductiveness or inductance present in the circuit, the current lags the voltage, right? So it is the inductance that is responsible for the low power factor, right? Now, but what will happen if we have low power factor, right? What are the disadvantages of having the low power factor, right? So let us understand that what are the limitations, what are the disadvantages of having low power factor in the AC systems or electrical systems, right? Now, if we talk about a single phase supply or a system with single phase, the power is given by VLIL into cos phi. So for any general AC circuit, for any general AC circuit, the power is given by P is equal to VI cos phi, or you can say cos phi is equal to the active power, which is nothing but P, and the apparent power, which is nothing but VI, right? So you can relate it here also. So cos phi is equal to P by VI, right? Or we can say that I is equal to P by V cos phi, right? So if P and V are constants, then I is inversely proportional to cos phi. Right? So that means if we increase the power factor, the current will reduce. Now which current? Load current, right? So if we rearrange this equation in such a way and we assume that this P and VL are constant, then we can say that load current is inversely proportional to cos phi, right? Now this is one thing, right? So similarly for a three-phase circuit, in both the cases, as you can see, in both the cases, the load current is inversely proportional to the power factor. So this means that if the power factor is low, then high value of load current will flow into the circuit, and vice versa is also true. That means if the value of power factor is high, uh, in that case, the load current will reduce, and low value of load current will flow in the circuit, or you can say low load current is required in that case, right? Either the current requirement would be high or current requirement would be less. That it depends upon the value of the power factor, right? Uh, so the ideal requirement is that the power factor should be unity. That is, cos phi should be equal to 1. This is what we call as unity power factor. However, this is the ideal case. So if the power factor is less than unity, then it has certain disadvantages. And these disadvantages are like, the first disadvantage is that the kVA rating of the equipment will increase, right? This is the first disadvantage, larger kVA rating. That means the source, right? The source will have more kVA rating. Now understand kVA rating, kilovolt ampere rating, kilovolt ampere rating, right? So this is the unit of the source power, apparent power, right? So that means the equipment, the device, the machine which is producing the source power or apparent power. So if the load current increases, that means due to the low power factor, if the load current increases, so it means the requirement of load current has increased. Now who will fulfill that requirement? It is the source that will fulfill that requirement. So that means to deliver a high value of current to the load, the size of the uh, machine, electrical machine, or you can say alternator, shall be large. So this will lead to the increase in the size of the electrical machine, and hence if the size increases, obviously the cost of the machine will also increase. Then the second uh, disadvantage of having low power factor is that the size of the conductor will increase. Now why is it so? What is the reason, right? Now let us understand that. Now in this case, now as we are saying that if the cos phi is low, so we'll write it here. If cos phi is low, then IL is high, right? It is as simple as that, right? Now, if IL increases, the resistance offered by the conductor must be low. So we have to keep a low resistance of the conductor. Now how will we keep the low resistance? So we have simple formula, R is equal to rho L by A. So that means if rho and L are fixed, so R is inversely proportional to A. So that means if the cross section is high, then the resistance will be low. So that means we will be using the conductors of larger size, larger cross section, because in that case only we will be able to get the low resistance of the conductor. Now the reason of getting low resistance is to reduce the I square R effect. This is one reason, right? So if the resistance is not reduced in proportional to the increase in current, so in that case what will happen, more I square R effect will be there, and hence it will lead to the um, malfunctioning of the machine, malfunctioning of the device, damage of the device, destruction of the device, like that, right? Then the next limitation is larger copper losses. As I discussed, if I increases, so in that case, I square R will also increase. For example, in case of a transformer. So in transformer, we have two types of windings, the primary winding and the secondary winding, right? So these windings have some resistance, which we call as winding resistance. So if due to the low power factor, right, this current, load current will increase, so the copper loss, the winding loss, IL square R across this winding will increase in the secondary current, right? If this is the primary winding, this is the secondary winding, secondary side, primary side, right? So if the load current increases, this will lead to the increase in the primary current also. So that means we will have the larger values of the copper losses in the primary and secondary as well, right? Both. So increase in the load current will lead to the increase in the copper losses in case of electrical machines or transformers, right? Then we have poor voltage regulation. Poor voltage regulation is again like, if we um, talk about the secondary winding, let us take the secondary winding here, right? So we have a resistance, we have an inductor here, right? And then we have a load connected here, right? So this is the load, right? Now this is the secondary current, so let us mark it as load current IL. This is the secondary induced voltage E2. This is the terminal voltage V2. This is R2. This is X2, right? So if this current increases, so it will have more voltage drop here, ILZ, right? This is the voltage drop. So more voltage drop will be there, right? Right. More voltage drop will be there, ILZ, right? Okay, so now, so ILZ, so this is the voltage drop. Now, if this voltage drop will increase because of the increase in load current, so this E2, so V2 is equal to E2 minus this ILZ. So this, if this increases, V2 will decrease, and E2 and V2 will have more difference. So in this case, the voltage will not be able to regulate, right? Okay, so as per the requirement, the voltage will not be able to regulate, right? So this is the one thing, right? And then we have the uneconomical system. Now this is very important because uneconomical means, so a low power factor leads to the financial penalties, right? So if the power factor reduces, it will lead to the financial penalties. Also, it leads to the high electricity bill, right? So if the power factor is low, large current will flow. Large current means, so low power factor means large current, means large units, right? So more electricity bill, right? So this is what happens when the power factor is low, right? So now, so disadvantages which I have just discussed have been mentioned here, right? So all the disadvantages are there, right? So now reduced handling capacity of the system. So with low power factor, it is quite difficult to handle the electrical systems, right? Because the current increases, and increase in current leads to many other, side effects in the electrical systems. Now, as I already discussed, what are the causes of low power factor? The primary cause is the inductiveness, right? This is the primary cause of the low power factor. It is the inductiveness of the load, right? Inductiveness of the electrical systems, right? So because of the inductiveness of the load, it is the current which lags the voltage by some angle. So uh, the angle between voltage and current increases, so cos phi will decrease, right? Now, lagging of the current from voltage will lead to the lagging power factor, and uh, this lagging power factor is the this lagging power factor is the reason of all those limitations which we have just discussed in the previous slides, right? Now, it is the inductive load which is responsible for the low power factor. It is the three-phase induction motors which are the inductive loads, the transformers, the lamps, the welding equipment, all these, because these all equipment operate at low power factors. They have more lagging power factors as compared to other, equipment, right? So we can use power factor improvement techniques to improve the power factor. Now, improving the power factor does not mean to make the power factor unity or more than one. Power factor cannot be more than one. Improving the power factor means to, enhance the value of power factor from the current value due to the inductiveness to some new value, okay, and bring it near to one. The purpose is to bring the value near to one. So these all are responsible for low power factor: the induction motors, the transformers, the welding machines, right? Now, how we can improve the power factor? This is the next thing we will discuss. Okay, so there are three methods by which we can improve the power factor of an electrical system. And the first is we can use the capacitor banks or static capacitors, right? We can use synchronous condensers. Synchronous condensers are nothing but the synchronous motors. And then we have the phase advancers also, right? So the first is how we can improve the power factor using static capacitor. Okay, so the capacitor banks are used like here we have a three-phase load and three-phase supply. So either in delta connection on star or in star connection, we can make use of capacitors. We can connect this capacitor into the system, right? And these capacitor, what they will do, they will reduce the value of this phi between the voltage and current, because our purpose is to reduce this value of phi. Our purpose is to reduce the phase difference between the voltage and current, right? Now we know that in case of an inductive load, the voltage leads the current by some angle phi, or you can say current lags the voltage by some angle phi, right? Now these are the static capacitors, right, which can be used. Now if we connect a capacitor, in parallel to the load, right, what will happen? So the current which is provided by the supply earlier, which we were saying that it is nothing but I1. Now this I1 current is still flowing in the load, but now the supply current will have one more component, which is the capacitor current, right? Now we have resultant of these two currents now, right? Okay, so that is, let us say, I2. So I2 is IC plus I1, right? So it is the resultant, right? Now if we draw the phasor diagram here, right, if we draw the phasor diagram, so it is a voltage that will remain same, because the voltage across capacitor is V and the voltage across this load is also V, because it is a pure parallel circuit, right? Now earlier the phase difference between V and I1 is, let us say, phi 1. Now by adding a capacitor in between in parallel to the load, what has happened? The phase difference between the voltage and the current, the resultant voltage and the resultant current, right, I2, has reduced, because the capacitor, okay, the phase difference between the voltage and capacitor, in this case you can see the current has, now this is not a pure capacitive circuit, it is still a combination of RLC. But here what has happened, just by introducing a capacitor in parallel to the load, what has happened? The current I2, which is nothing but the resultant current, this I2 has shifted towards the voltage. Now in this case, this phi 2 is less than phi 1. If phi 2 is less than phi 1, then cos phi 2 is greater than cos phi 1. So that means by introducing a capacitor or a static capacitor in the circuit, the power factor has increased. Okay, so our purpose was fulfilled, and the purpose was to reduce the phase angle between the voltage and the current, right? And then we have the synchronous condensers, right? Now in the synchronous condensers, how we improve? So in this, the synchronous motors are actually used, right? Now what the synchronous motors do, they are actually made to operate at no load conditions, and they are overexcited, right? Now in this case, these synchronous motors, now when they are overexcited, so they start providing the leading current, right? They start providing the current to the supply, and they start acting as the capacitor. Okay. Now, when we connect a synchronous condenser, you know, across the supply in parallel, actually. So now, what it will do, it will try to draw the leading current, and it will eliminate the reactiveness. That means, uh, you know, it behaves as a capacitor. It behaves as a static capacitor, as we discussed in the previous slide. So by doing so, what will happen? The power factor will definitely improve, right? Okay, so the synchronous condensers are used in the large industries where we have large machineries, large power rating devices used, right? So there we make use of synchronous condensers to improve the power factor, right? Now, as you can see here, it is used in the similar way with the supply. We have a supply here, we have a three-phase load, we have a synchronous motor, which is used as synchronous condenser. So it will draw the magnetic component of the current. it gets overexcited and start supplying the leading current to the load, right? And in this way it will, you know, reduce the, earlier the phase difference between V and I was this one. Now it will reduce the phase difference between the voltage and current by drawing the magnetic component of the current, right? So the phase angle has reduced and hence the cos phi, that is the power factor, will increase, right? Then we have phase advancers. Phase advancers are nothing but the AC exciters which are used to improve or enhance the power factor of the induction machine, induction motor specifically. So it is purposefully used for the induction motors only, and it is mounted on the shaft of the motor and it is connected to the rotor circuit of the motor, right? Now, its purpose is to provide the exciting ampere turns. Exciting ampere turns mean exciting magnetomotive force to produce the required flux. Okay, so if any, so it basically provides flux by generating the magnetomotive force, and through that flux, it improves the power factor, right? So if we can increase the ampere turns, that is magnetomotive force, so we can make the machine, the induction motor, to operate at leading power factor. Now let us see this picture here. Okay, so when we have the lagging power factor, so the first picture shows you the lagging power factor. You can see here. Okay, so blue line, blue wave is for voltage, green wave is for current, and this shaded region, this one is a waste, right? So as in case of inductive loads, right, the current lags the voltage by some angle. Okay, you can see here the current and voltage are lagging from one another, right? So there is a significant phase difference, right? Now you can see this is nothing but the waste. Okay, so what we have to do, we have to reduce the gap between voltage and current, right? So this can only be done by any of the three methods which we have just discussed. Now when we reduce, when we are able to reduce this gap between voltage and current, what will happen? The waste will reduce. The waste has reduced here. So the second figure you can see, it is when we have corrected the power factor, when we have improved the power factor. The first figure is when we have not done the power factor correction or improvement. So you can see the difference and you can understand that what are the benefits of improving the power factor. So this is one benefit, the waste will reduce, and also the enhanced power factor will lead to the low requirement of the current. Less current means less low I square R effect, low voltage drop, high voltage regulation, small conductor size, small kV rating. So all those disadvantages which we discussed previously in the last to last slide will eliminate or reduce to significant extent, right? Okay, so the capacity of the system will increase, voltage will increase, voltage regulation will be better, right? And losses will be less, right? And efficiency will be high. So this was all about today's lecture, and thank you so much.